All right, let's dive in. We're looking at, well, basically the bedrock of modern AI today. That 2017 paper, Attention is All You Need. It's kind of the genesis point, wouldn't you say?
Oh, absolutely. It's hard to overstate the impact. You mentioned the citations over 173,000 now. It really kicked off the current AI boom you're seeing everywhere.
And it came from just 8 researchers at Google Brain and Research, which is kind of interesting. They were all listed as equal contributors.
Yeah, that was a nice touch. And they had a bit of fun, too. The title, like you hinted, it's a play on the Beatles, All You Need Is Love.
Right. And I heard something about early designs using characters from the actual Transformers franchise.
That's the fun fact. Yeah, little nods here and there.
Yeah.
But the core idea, that was the serious part, and it was pretty radical.
Totally radical. Their main point was basically, let's build a network just using attention. No more of the usual suspects like RNNs or convolutions.
Exactly. They wanted to completely ditch recurrence, which, at the time, RNNs, LSTMs, GRUs, they were sequence modeling.
So what was the problem with those older models? Why ditch them?
The fundamental bottleneck was time. They were sequential. To figure out what's happening at, say, word 5, you absolutely had to process words 1, 2, 3, and 4 first.
Step by step.
Step by step.
Yeah.
You get this ON, time dependency. The longer the sequence N, the longer it takes. And critically, you couldn't really parallelize that core computation effectively on GPUs.
Okay, so the transformer gets rid of that sequential waiting game.
Precisely. It trades that time dependency for parallel computation. With self-attention, every single word or token can look directly at every other token in the sequence simultaneously.
And basically one step.
In a constant number of operations. O1, yeah.
Yeah.
Regardless of how far apart the words are. So that whole problem of forgetting the beginning of a long sentence,
Long-range dependencies.
gone, or at least drastically reduced.
Yeah.
The architecture itself allows direct connections.
And this wasn't just theory. The results were, well, they were pretty stunning, weren't they? State-of-the-art on translation tasks.
Smashed the benchmarks. Like the WMT 2014 English to German translation task, they beat the best existing models by a significant margin, like 1 or 2 BLU points, which is huge.
But the training time, hang on, was it really just 3.5 days on, like 8 GPUs?
Yeah.
For the state-of-the-art model?
Which was, frankly, revolutionary. It wasn't just a better model, it was exponentially faster and cheaper to train than the previous best systems. That lowered the barrier to entry massively.
Okay, let's get into the mechanism. The engine is scaled dot product attention, using query, key, and value matrices. Can you break down what QK and V are actually doing?
Sure. Think of it like this. For each word, the query, Q, is basically asking a question. How relevant am I to all the other words?
Okay.
The keys, K, are like labels on all the other words, saying, here's what I'm about. And the values, V, contain the actual information, the substance, of those other words.
Ah, so the query matches against the keys to decide which values are important.
Exactly. He calculates a score between the query and each key, scales it, turns those scores into weights using softmax, and then uses those weights to create a weighted sum of the values. That's the attention output for that word.
And then they layer on multi-head attention. Why multiple heads?
Right, so instead of doing that QKV lookup just once, they do it multiple times in parallel, say 8 times, with different learned QKV matrices for each head.
What's the point of that?
Each head can learn to focus on different kinds of relationships. Maybe one head looks at syntactic links, another looks at semantic similarity, another focuses on nearby words. It lets the model capture richer, more diverse connections simultaneously.
Got it. But you mentioned attention itself doesn't inherently know about word order. If you just have attention, the cat sat on the mat looks the same as the mat sat on the cat, right?
Precisely. Pure self-attention is permutation invariant. Order doesn't matter. That's obviously a problem for language.
So the fix.
Positional encodings. They had to kind of manually add information about the position of each word back into the input embeddings. They used fixed sine and cosine functions of different frequencies. It's a bit of a patch, but a necessary one.
Okay, so this architecture lands, it's powerful, it's fast to train, and then what happens? It seems like it immediately splits things.
Yeah, the original encoder-decoder structure kind of fractured almost right away, defining the 2 main paths we still see everywhere in AI research.
Right, path 1, encoder-only models, like BERT.
Exactly. BERT uses the encoder part. It looks at the entire input sequence at once by directional attention. It's great for tasks where you need to deeply understand the context of the whole sentence, like classification or finding names in places. NLU tasks.
And path 2, decoder only, the GPT family.
Yep. GPT uses the decoder part. Crucially, it uses masked self-attention, sometimes called causal attention. It can only look at the word that came before it in the sequence.
So it generates text one word at a time, auto-aggressively.
Right. It's optimized for generation. Chatbots, writing articles, generating code. That's its strength.
It's fascinating how quickly this idea jumped domains, too. It wasn't just for language.
No, that was maybe one of the biggest surprises. The Vision Transformer, or VIT. People realized you could take an image, chop it into, say, 16 by 16 pixel patches, treat that sequence of patches just like a sequence of words.
And feed it into a transformer.
And feed it into a standard transformer block. It worked incredibly well, directly challenging convolutional neural networks, CNNs, which had dominated computer vision for decades. It showed the transformer was kind of a general-purpose relationship processor.
But there's always a trade-off, right? The power came at a cost.
The Achilles heel, yeah.
Yeah.
That out-end complexity. Because every token attends to every other token, the computation and memory requirements grow quadratically with the sequence length n.
So double the sequence length, quadruple the compute needed.
Roughly, yeah. That's the main bottleneck stopping us from easily feeding entire books into these models. It gets incredibly expensive for very long sequences.
Yet the core architecture, the transformer block itself, is still what powers almost everything today, isn't it?
Overwhelmingly so. That ON problem hasn't really been solved by finding a fundamentally different architecture that scales better, not in the mainstream LLMs anyway. Instead, it's been tackled through brute force scale, more hardware, and clever engineering.
Like flash attention.
Exactly. Things like flash attention don't change the quadratic nature, but they optimize the implementation incredibly well, especially how data moves between GPU memory levels, making it practically much faster.
Okay, so wrapping this up for you, the listener, the paper's title, Attention is All You Need, maybe isn't strictly true today. We need positional encodings. We need stable normalization layers like layer norm or RMS norm. We need things like rotary positional embeddings, ROPE.
Right. The architecture has evolved. But the central, really defiant claim of the paper that recurrence is not necessary, that idea absolutely holds. It was the spark, the Big Bang.
It proved a foundational element wasn't needed, which leaves us with a final thought for you. What core architectural assumption are AI researchers making today? That might seem essential now, but that the next generation of AI models could prove is completely unnecessary. What's the next recurrence we're all relying on?
Yeah, what fundamental piece are we maybe blind to? That's the big question looking forward.
Definitely something to think about.